Okay, puppet. Oh, wow, you're really close. Let me move you back a little bit there. Come on, a little personal space here. COVID, what are you doing? All right, let's pull you up a little bit, get you on. Okay, all right. Now, in the last video, I was doing a real quick drawing of diffraction, and my lines didn't exactly, do. So this time I just said, all right, let me do this again. We'll start off this video. We're going to do math. This is going to be the diffraction grading math today. Well, now. And I made this a little bit better, and I drew it with blue, you can see that, right? Yeah, you can. Blue marker coming from this opening and red marker coming from this opening. And I did it a little more carefully, and so the crests would overlap in a straight line pattern. So in other words, where you can see these red dots, all right, that's where a blue line and a red line are overlapping. Blue line and red line are overlapping, blue line and red line overlapping, blue line and red line overlapping. So what I ended up getting, you can see, I think you can see this. You kids are relatively good vision, okay? We can see that where a blue line and a red line crest overlap, I get a straight line pattern, and it points to, boom, over here would be that piece of paper on the wall or something you're projecting the light onto. And I get a bright spot where those two are overlapping. If you get two crests overlapping, that's constructive interference. So we have two phenomena going on when we have the Young's diffraction experiment. We have diffraction, and then it results in interference, which gives us our pattern. We get a bright spot right here in the middle. I've got those crests overlapping, and I get a nice big bright, you saw it over there, a nice big bright red spot there. Bright red, and then here I have another straight line going out to this bright spot. And then what I also did is I put some black dots where a crest of one of the waves, and here it's red, overlaps with the trough between the two blue lines. So we have a crest and a trough overlapping, and here I have a crest and a trough overlapping. Here it is, crest and trough, crest and trough. And when I have the crests and the troughs are harder to see, like for example, in this dot right here, I have between these two red lines, that would be the trough in between these two red lines, but yet there's a blue crest there, so that would be a crest and a trough overlap, and when you get that, you get destructive interference, and that would be, when it comes to light, that would be dark. So over here on the wall, we saw alternating bright spots and alternating dark spots. Not dark spots again, it's just dark area where the light is canceled and you don't see anything. So that's just a little bit better drawing. It took a little more time to draw that out for you, and hopefully it helps. Now, it's not really that important that you can draw that. I'm not going to ask you to draw that out. I mean, it's hard. I have, I went to high school in the 1930s when I learned this, and it was hard then. Like 20 years later. What are you, in the 50s now? Yeah, still hard to do. So I wouldn't expect that, but I just wanted to show you that these, when they do overlap the crests, you will get a bright spot. They do point to a bright spot that we saw on the wall, and when the crest and a trough overlap, you get a dark area. Okay, so that's how come we get the pattern. Now what I've done here is I put a B for bright, B for bright, B for bright, D for dark, dark, dark. And over here you'll see that it says max equals 0. That central bright spot is called the 0 maximum point. And I'll circle that. It's my bright. And then every bright spot, and they are equal distances on either side of the central maximum, I put a 1 because that would be called the 1 maximum, the first maximum away from the central maximum. That's what it means. And here, the first maximum, a bright spot away from the central maximum. Now down here, you can see this. We have B2. The second bright spot away from the central maximum. Again, equal distant between the bright spots. And up here, we also have a central, 2 away from the central, so that's called a B2. So B2, B1, 0 maximum. And in between those, we have those dark spots. Okay, now over here, I've labeled a D. The D is for the distance between the centers of the two slits. The center of the two slits which are diffracting the light, that's D, the distance between those two centers. And then down here I put an L, that's the length, or how far it is from where your slits are to wherever you're projecting this, like I did it on the wall. For me, that was like 9 feet. But of course, you can have that projection being a lot closer than that. But that is the distance between where you're projecting it and where the slits are. Okay, so that's the setup. Now over here, You can kind of see, we'll get it in better view there. We have an equation, d sine theta, and this is the one that I was showing you earlier, right there on the sheet for optics. Where are we there? There we are, right there. There we are. That's that equation there. And it says d sine theta times m times lambda. And what is that? That's the Young's experiment equation. So this is important. Now, I'm spending an entire video. Actually, this is like, think about it, it's like a third video. I showed you the phenomenon itself. Then I went over kind of how it works, and then I went over how it works again with a better drawing, and now we're doing math with it. That's a lot of time. And the reason I'm doing that is because AP loves Young's experiment, loves it. It's one of those historical experiments that they're just like, bam, you better know it, you physics people. It's kind of like photoelectric effect. They love that one too, and we'll get to that later in the year. They love that. They love these classical experiments that change things, change the outlook on what life is like in the world of physics. And this did that. That did that. This is like, dude, you might think light's a particle, and whatever, but it is a wave, man, or at least it has wave properties. Boom, definitive. This is one of those experiments. AP loves it. It shows up. It shows up. If it's not an FRQ or a portion of it, which you got about going back about a 33% chance of that happening, it definitely shows up in questions and multiple choice. It absolutely does. See, that's why I got to know how to do it. Okay, so that's why I spend so much time on this, is because one thing. All right, spent a lot of time babbling, so let's get going. So here's the equation. Gets a little better view here. Boop, 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 boop. Oh, wrong way. There we go. There we go. All right, now here is in the equation D, the distance between the slits, sine theta, explain in about 10 seconds, m, which refers to, that's a number, it's an integer, it's a number which refers to which bright spot we're at. If it's the middle bright spot, that becomes 0. If it's the first bright spot to the left or right of the center bright spot, that's a 1. If it's the second bright spot away from the center, that's a 2. If it's the third bright spot away from the center, that's a 3. I think you get that. It's a whole number for constructive interference. So we have bright spots are constructive interference. That's a 1, a 2, a 3, a 4, or a 0 if it's the center mark, which of course this whole thing just goes away. But now this is wavelength, the wavelength of the light that you're using. Okay, so those are our things. What's this sine theta thing? Yeah. Okay, I'm going to kind of break up my drawing a little bit. I know, I'm kind of sad to do this because it kind of took me a little time. Sad, but I'm going to take it away. So clear this out. Bye-bye. Bye-bye. Okay, take this out. Clean it up. And show you what the sine theta thing is. Now, these two slits are so close together. They're so close. They're like a fraction of a millimeter apart. And that's not very far. So, for all intents and purposes, what we do in calculating is we use the center between the 2 points. And I'll actually draw that out to the first maximum. And that angle is going to be the sine of the angle. If I wanted to take a line and put it to the first bright spot, or the second bright spot from that point. So I've got a spot right in the middle of the two. Actually, technically what you do is you measure it from the center of the opening, to those bright spots. But since these are so small, it's an insignificant, in the math, it'll be an insignificant difference. So for ease, we put the center, the point where I'm going to measure this angle from right in the middle of the two spots. Okay, so now from here, this is an angle. Across the center maximum, out to the first bright spot is an angle. That's theta. So the sine of that angle sine of that angle to the first bright spot would be that angle here. Now, if I'm using the second bright spot, m equals 2 out here, then that angle would be that. That would be the sine of that angle here to the second bright spot. So the sine of the angle is measured from the center of the two slits to whatever bright spot or dark spot. You can do this with dark spots, dark areas. I keep saying dark spot, oxymoron. Dark areas as well. So that is how we measure that angle. From the center of the slits to whatever spot that you're looking at. Okay, so let's go ahead and use this equation in an example problem. Example problem here. I've got an example problem kind of set up over here on the board. So I'll get rid of this. Okay. Oh, here we go, kids. Here we go. Something muy importante, grande, is this. And to do the problem set that's going to be due with this, you need to know this. Okay, listen up. Wake up. Wake up. Are you awake? Oh, I didn't mean booing that you're awake. If you're awake, it should be, yay, you're still awake. Okay, good for you. Good for you. Because, man, if I were you, I'd be going, drool coming out. Okay, but this is important. You need to know this. Write it down. Write this down. Because you won't remember it. You won't. Yes, I will. No, you won't. Write it down. When it comes to very small angles, and these angles are really small. Small openings. These patterns, these are small angles. These angles are, when we're doing the math, usually going to be under 10 degrees. Okay, small angles. Here's what's true. And I'm going to show you, because you should not believe me, that the sine of an angle, if the angle is small, is wiggly equivalent to the tangent of the angle. Sine of the angle is wiggly equivalent to the tangent. What does that mean? That means they're equal? No, they're not quite equal, but they're pretty close. That we can assume. Now, your math teacher doesn't like this, but too bad. Too bad, TB. Too bad. Terry, Captain Radiant, yeah, too bad. Yeah, you should have them on my videos, Terry Barely, so that they hope you're happy about that. But you should be, because millions of people are watching this. So, sine of an angle for a small angle is essentially the tangent of the angle for a small angle. You might say, well, so what? Well, who cares? What difference does that make? Well, check it out, check it out, check it out, check it out, check it out. If I draw that line across here, and I know the distance from that center maximum to the first maximum. This L is one side of the triangle, and this is called Y, the distance between the two bright spots. D is the distance between the two openings, but Y, we call this Y, is the distance between the two bright spots. Then, hey, check it out. And that's what we can measure. We can physically measure that. If we had a ruler or a meter stick and I went over to that thing on the wall, we could have physically measured the distance between those two bright spots. Okay, physically can do that. Measure that, and we can measure the distance from the laser to the wall, which I mapped out to be 9 feet. So we can get what this angle is if we use tangent, the distance here to the distance here, which is easily measurable, non-diffraction gradients, when they show up. That means the tangent of this angle here can be used to approximate the sine and put into our equation. That becomes handy-dandy notebook, people, when you're doing the math on this. Handy-dandy notebook. Blue's Clues. Blue Skidoo, you can too. I should have been that guy on that show. I would have kicked butt. Okay. So in other words, some of you told me math purists. Oh my God, you can't do that. You can't do that. Yeah, you can. I'll prove it to you. Okay. Don't trust me. I mean, me. Let's take a little calculator here. Turn it on, and let's go sine of 4 degrees. 4 degrees. Small angle, right? Sine of 4 degrees. Let's go hit enter, and it's point. You can see it there. Don't trust me. 0.0697, so 0.0697, we'll round that 7 off, so we'll go 0.0698, 0.0698, 0.0698, that's the sine of 4 degrees. Let's do tangent. Okay, tangent 4 degrees, okay, tangent 4 degrees, you can see it, don't trust me, 0.0699, so that rounds to 0.0699. Okay, check it out. Okay, look. We're off by one blah, 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 blah in the 10,000th place. Okay, it's not going to make any difference in the math. It's good. We can use that approximation. That's going to come in a handy-dandy notebook when we're doing some problems with this. So because we'll be able to measure this and use tangent to be the sign in this. Now, of course, if we can get the sign, if we have the sign, then we use it. Because, it's a little tiny bit more accurate. Okay, so let's do a problem. Keep going here. All right, get you out of the way. I think at this point I can just kind of like obliterate this thing, right? I mean, we can obliterate this and do some math. Okay, go on. All right. Okay, over here, here's our problem. I wrote this down where it says, we're going to get you back here. The distance between two slits is 0.012 millimeters. Boy, that's really close together. We are looking at a pattern that produces, that we can see at least 4 bright spots out from the 0. So 0, 1, 2, 3, 4 bright spots on either side. The angle that's formed between D, I'll draw this out quick, is 10 degrees. What's the wavelength of the light that's causing that? So we can calculate the wavelength of the light. And quite often, that's what you do with this. They want to know what the wavelength of the light is causing this pattern. So here's what we got. We've got, bump, bump, bump. And that distance here is 0.012 millimeters. Remember that, millimeters, careful. And then over here, we got a pattern. This would be first bright, second bright, third bright, fourth bright, above. So that's 0, 1, 2, 3, fourth bright. That's confusing sometimes. The fourth bright spot is not the fourth bright spot, it's the fifth one because the 0 is the brightest spot. So we start from there, 1, 2, 3, 4. So that's this one. And the angle that goes from here to there is 10 degrees. Okay, what is the wavelength causing this pattern? So now we're ready to do some math. Finally, D, be careful. We've got to be in meters. Remember, meters, physics, meters. So that is 0.000. Now this is millimeters, so we got to move it milli, 1/1000. We've got to move it 3 times. Boom, boom, boom. So I got to add 3 zeros. 0, 1, 2 meters. All right, so that's where we were here for the millimeters, and then we go 1, 2, 3 for the meters, small number. What do we got? Sine of the angle. So we need the sine. Now we were told what the angle is here, so we're going to use sine, not tangent. We were told it was the angle. You're going to use that tangent thing. They'll use that when you don't know what the angle is, but you have measurements to calculate it. Here we were given the angle, so we use sine of the angle. Now, if you use tangent, you'll get about the right answer anyways, but use sine if you have the angle. Sine of 10 degrees, right? 10 degrees, yeah. Is equal to m. Okay, what do I use for m? 2, 3, 4. I use a 4. It's the fourth bright spot, so use 4. And then wavelength. So let's do the math. Okay. So 0.000 0.012 times the sine of 10 degrees. So I'm going to hit enter on that, get an answer, and divide by 4. Divided by 4, and I get 5.209. So we'll say 5.21 times 10 to the negative 7th. 5.21 times 10 to the negative 7th. This is just an integer. This is in degrees, so no units here, no units here. So boom, the only unit you had was your meters. So that wavelength, length should be in meters. And that's in the visible light spectrum. That's what we can see is on the order of 10 to the negative 7th with visible light. So this would be some visible light. Now you can look it up on a chart and see what exactly the color that would be. You can look it up, get the color. So that is one way to use this thingy here. Okay, let me do one more quick problem here for you. And then we'll set you free, because I know you're all going, oh my God, you add up all these videos, it's like 10 hours. Stupid Young's experiment. I know, I get it. I think it's kind of cool, but I get it, I understand. I understand your angst. You're teenagers, you're all angsty. Okay. All right, well, what if we had the following? Oh, on our sheet, you also have the equation here, and this wraps up the whole equation for this unit, so you know what's coming. Yes, you do. You know it's coming soon. And it is. Yeah, it is coming soon. You know it. This one here, okay, if you can use the length that we have between the screen and the slits. You can use that to do some stuff too. So that comes in handy dandy notebook sometimes. That's the length between that screen and the slits is equal to ML. So this here, go back to this. So let's go ahead and put this up. Some slits here, screen, you know L here, so that's L here. Okay, and you do this, and maybe there's a bright spot, big bright spot here, bright spot here, bright spot here. And that angle here is theta. Okay, and that's this side is a particular maximum. So, 1, 2. So you can go ahead and use this instead of an angle if you know that length in here between the two screens. And so that takes up the D, okay, the distance between the screens, sine. And there's, you can go ahead and use that sometimes. It comes in handy dandy notebook. But not often, but sometimes there'll be a problem set up like that. And I don't want to do a problem like that, so that's an uncommon problem. Let's go ahead and do another problem. Okay, what we got? I'm having so much fun. Are you having fun? You kids having fun? This is going to be a long video, and you're getting going here. It's 21 minutes. Stop babbling. Move. Okay, so let's say that you know that, oh. I know you're going to hate me for doing this. Sorry. But this D for small angles, small angles, anything under, I'd go 10 degrees. Anything more than 10 degrees, it's not good, but most of these angles are small anyways. Anything under 10 degrees, we can do this. We can substitute in tangent of theta for anything under 10 degrees small angle. And tangent is equal to the opposite. Remember, tangent is equal to the opposite over the adjacent. So the opposite side we call y. That's the distance between the bright spots. Okay. And the length, the opposite of the adjacent, L, equals m theta. So this is kind of a useful one at times if you don't have the angle, if you don't have it. And but maybe you need to find out what the length is, or you need to find out the distance between the slits, the distance between, the slits is here, but the distance between the bright spots. You might be asked to find that kind of a thing, and this really helps, this version of it. Of course, it's not on your handout. They expect you to kind of know that. They expect you to be able to go, wait a minute, sine into small angles and tangents of small angles are the same, so then the opposite over the adjacent, the distance between the bright spots and the length between the plates, the diffraction grating and the projection. Okay, so that comes in handy. So let's say that you knew the length between, okay, where the diffraction grating is and where you're projecting is, let's say it's 1 meter. 1 meter away. And you know the distance between the slits is 0.00002, okay, 1, 2, 3, 0.02 millimeters, 0.00002 meters. And, okay, so let's make the, and you want to figure out what the distance will be between two bright spots. So the distance from, let's say this is the center maximum. And you want to know what the distance is from here to the second bright spot. So you want to know that distance between the center maximum, the brightest spot, and that bright spot, two bright spots away. You want to know the distance. You don't know what it is. You want to know what that is. That's why. Okay. So that would be a 2 here, because you want to know the distance, the second one. And you know the wavelength of light you're using? You have to, otherwise you have 2 unknowns here. So the wavelength of light you're using is maybe 4 times 10 to the -7th. It's in the visible range. So now you can figure out what that distance is by using this idea of tangent is equal to that opposite side, which is y over the adjacent side, which was L, which was 1. You can do the math on this. Okay, you kids are relatively intelligent. You can solve for y, multiply by 1. Didn't do anything. Divide this by 0, 0, 0, 0, 2, and you will have that distance between those two bright spots, that maximum and the second bright spot. So let's do it out. I know you're so excited. I'm so excited for a long video of this stuff. I know you can see the excitement in your face. I can say, Ian, wake up. Ian, wake up. I can see you back there making a breakfast sandwich when you should be paying attention. All right, okay. All right. Declan, are you awake? Are you awake? Wake up, Declan. Wake up. Okay, thank you. Here we go. So this is going to be 8 times 10 to the negative 7th. 8 times 10 to the negative 7th divided by 0, 0, 2. So let's do 8, second function exponent, negative 7 divided by 0.2. And then boom, 0.04. Y is equal to 0.04 meters or 4 centimeters away. So that means between the big bright spot and 2 bright spots away, it'd be 4 centimeters. Makes sense. Actually, that's about what it was on our wall over there a long time ago, like forever ago that I showed you that video. It was about 4 centimeters away. 4 centimeters about that far. So, boom, 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 4 centimeters, second bright spot. First bright spot. Oh, we have to calculate that one too. No, it would just be half of that. Okay, it's a repeating pattern. So the first bright spot would be 2 centimeters away, then 4, then 6, then 8, and so on. Oh, this is a long video. It's going to take me a long time to upload this to YouTube. YouTube doesn't like long videos. I'm sorry. I apologize for the longness on this, but it was muy important. Muy important. Put your finger in there. Do it. You won't do it. Sorry. All right, that should wrap up this unit on this little subunit and ending the unit on optics in light. Very important ending. Took a long time. It took me like 40 minutes to go through this. And if we were in class, it would have taken me the entire class to go through this easily, and it did. Okay, kids, bye.